continue. So this chapter is cover quite a few topics, okay, that will be put in another way, okay, very useful in many areas, okay. The most important concept in this chapter is eigenvalues. What is eigenvalue? Okay. So, the first section, okay, eigenvalue and eigenvector, okay. So if you have a matrix A, n times n matrix A, a scalar lambda is called eigenvalue of A if there exists a non-zero vector x such that Ax equal to lambda x, okay. So in other words, okay, you multiply x with this matrix A, okay, it will either enlarge or shrink this same vector. The result is like you are going to get the same. The result is going to be a vector of the same direction. Okay, that's what we meant by this eigenvalue and eigenvector. The lambda and the x, okay, lambda is called eigenvalue, x is called eigenvector. Okay, and obviously lambda and x have they have a tie, right? I mean, if you have a certain eigenvalue, I mean, you may have like some eigenvector associated with that, okay, and so the value x blah 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 blah, okay. So the eigenspace corresponding to lambda is the collection for all eigenvectors belonging to lambda and the zero vector 0. Okay, what do we mean? Okay, because okay, for a given eigenvalue, you may have more than one vector, more than one eigenvector, okay, or you have no eigenvector, okay, for that eigenvalue. Of course, that's, I mean, but if you have some solutions, you may have one, you may have more than one. So the space spanned by those eigenvectors is called eigenspace, or corresponding to that particular eigenvector, particular eigenvalue. Okay, so if lambda is the eigenvalue of a matrix A, the eigenspace corresponding to lambda is a vector space. Can we prove that? First, I mean, how do we prove something is a vector space? Vector subspace, okay, because obviously, I mean, here, I mean, we are talking about like a n-dimensional space, right? A subset of that n-dimensional space. I mean, the n-dimensional space is a vector space anyway, right? So it's a subspace. So how do we say something is a subspace? Huh? Do you guys still remember? Basically, it's like if you have like some vectors belonging to this space, the linear combination of these vectors will still be in this space. That's what we meant by a subspace. Okay, so if V1, V2 belong to this V, we have to show alpha V1 plus beta V2 belong to V as well. Okay, so so because we are talking about eigenspace, right? So for lambda, so if V1 V2 is in V, that means like A v1 equal to lambda v1, right? And a v2 equal to lambda v2, right? That's what we know, right? Okay, so let's check if lambda v1 plus beta, alpha v1 plus beta v2 belong to is an eigenvector in this eigen space as well. Okay, so let's say A. Excuse me. A times lambda v1 plus alpha v1 plus beta v2 equal to, well, you do the math, that's very easy. Alpha times A v1 plus beta times A v2, right? Right? Just, you know, very simple, like a distribution law, and you know, and you get like alpha out of here and so on. So this will be, you know, this will give you alpha times lambda v1 plus beta times lambda v2. So it's going to be lambda alpha v1 plus beta v2, right? So far so good, right? So if so for given eigenvalue, its corresponding eigenspace is a subspace, okay, vector subspace, okay. Then, okay, the next question is, how do we compute the eigenvalue and eigenvector? Okay, so it's like this. If ax equal to lambda x, then we can, you know, move the lambda x to the other side, okay, and you know, lambda x can be considered as a lambda times I times x, right? Because A is a square matrix, right? A is a square matrix. So I, you just have n times n identity matrix, okay? So you convert the lambda x to be lambda times I times x. And then once you move to a left hand, the other side, and you can do like this. And then, okay, because this is like a homogeneous linear you know, system. So because here we want something that is non-trivial. I mean, for this you know, for this system, okay, we want a non-trivial solution for this system. So that implies the determinant of this A minus lambda I has to be 0, right? If the determinant of this is not 0, what does that mean? The only solution will be 0 vector, right? If the only solution is 0 vector, then you pretty much have no non-trivial solution, okay? So basically, okay, the determinant of A minus lambda I has to be 0, okay? So if that's the case, so the n degree polynomial, okay, P lambda, which is obtained from the determinant of A minus lambda I, okay, is called the characteristic polynomial for the matrix A. So you basically need to solve this polynomial, okay, to get all the possible eigenvalues, okay. So the equation determinant A minus lambda I equal to 0 is called the characteristic equation for the matrix A. So this, just remember when we say characteristic polynomial or characteristic equation, what do we mean? Okay, you need to remember. Okay, so lambda is eigenvalue of A if and only if lambda is a root of the characteristic equation, obviously, right? I mean, this is obviously the case. Okay, I mean, I don't know if this is really not much to show. Okay, because I mean, when you solve this, okay, obviously, okay, if lambda is a root, then it's an eigenvalue, and if lambda is eigenvalue, because it means lambda satisfies this equation, right? So in other words, okay, you move this to the other side, and it means like you have like the determinant of this must be 0. Okay, in other words, lambda is a solution. It's a solution of it's a root of the characteristic equation. So if lambda is the eigenvalue of A, the eigenspace corresponding to lambda is the solution of a n times n homogeneous system, A minus lambda I times x equal to 0. So this, I mean, just solve this homogeneous system to get like all the possible solution. Those will be your eigenvectors. Okay. Let's have a look at some concrete example. So this is A. So PA lambda, so you just, 3 minus lambda, 0 minus lambda, negative 1 minus lambda, and you put them into a determinant, and yeah, something like this. So the result will be, well, I think this is pretty easy, right? You just expand this determinant, and you will get like a lambda, polynomial, okay, of order 3, okay, and you can solve it, and which will lead to negative lambda times lambda minus 1 squared. So what does that mean? That means the solution for lambda will be 0 and 1, right? So when lambda is 1, okay, you put in here, okay, it will be your matrix A, okay, so it's like A minus 1, so A minus I, okay, times x equal to 0, right? So what you want to solve is like 2, 2, 2. Negative 1, negative 1. And negative 2, negative 2, negative 2. X equal to 0. So you can solve this homogeneous system, right? So obviously I go one. I don't think I need to show you how to solve this homogeneous system. And it should be trivial. So and by the way, this is obviously like a rank 1, right? Okay, and then the space, the solution space, will be 2, right? So which reflects, is reflected. In the solution, you have 2 eigenvectors for lambda equal to 1. For lambda equal to 0, okay, there's only one eigenvector, 1, 1, 1. Okay. So, yeah, this is. I think I can skip this pretty much. Basically, it's trivial. Okay. I mean, if because we are in chapter 6, okay, this is something you should have known from the chapter maybe 2, 3, maybe. So lambda 2 is 0. I mean, you get like its corresponding, you know, eigenvector. You know, just solve it. More example. Okay, again, a minus I lambda I, the determinant, okay, equal to 0. So you know, so basically it's like this. And if you try to solve it again, it becomes this one. Okay, and is it the same? Oh, it's slightly different, but I mean it's similar, very similar, very similar. So when lambda is 0, you get like a 1, 1, 1 as its corresponding eigenvector. When lambda is 1, you get 2 eigenvectors associated with that. Okay. So again, like this should be trivial. You can try to do it yourself. I mean, just pick an arbitrary example and try to work on that, and hopefully, like, I mean, you know, one example should give you like enough like confidence on this type of stuff. Okay. So here we have a theorem. Okay, that A be an n times n matrix and the lambda is a scalar. Okay, the following statements are equivalent. First, lambda is an eigenvalue of A. Okay, the second, A minus lambda I x equal to 0 has a non-trivial solution. So this, I think, like from first one to second one is so obvious, right? Because like, what do we mean by lambda is an eigen value? That means there exists a vector such that A v equal to lambda v, right? So obviously, like you get the second one like immediately, okay? And then the n A minus lambda I is not you know, the zero space. I mean, the n, what is n? N is n represent like oh yeah, this should be v not 0. Okay, I forgot to mention v is not 0. Okay, so n means the null space, right? Null space. So this sentence and this sentence are the same. A minus lambda I x has a non-trivial solution, and the null space of A minus lambda I is not just 0 space. I mean, these two sentences are equivalent anyway. So A minus lambda I is singular. What do we mean by singular? It means its determinant is non-zero, right? Okay. And sorry, determinant of that is 0. Is 0. Okay, it means it's singular. Okay, and the determinant A minus lambda I is 0. So these are very, very trivial properties, and obviously they are equivalent to each other. Okay. So, okay. The following theorems will be more and more interesting, okay, and more how should I say, like non-trivial or difficult to tell, difficult to observe, like later. Okay, so if lambda 1, lambda 2, lambda k are distinct eigenvalues of an n times n matrix A with corresponding eigenvectors x1, x2, blah blah xk. Okay, so this x1 to xk, they have different eigenvalues. Okay, then x1, x2 to xk are linearly independent. So how do we show that? So if you have two, for example, and so this is, if you have two vectors, okay, with two different eigenvalues, okay, can you show that they are independent? What is the definition of independence? Every time you want to prove something, you should always go back to the root, the definition. Okay, so because we want to show something like two vectors are independent, okay, then we always go to the definition of independent. Okay, the vectors are independent. So that means like if A if we have A1 x 1 plus A2 x2 equal to 0, we can derive A1 equal to A2 equal to 0, right? Right? That's what we meant by independence, right? Okay. So here, okay, for this one, we apply A on both sides. So A times A1 x1 plus A2 x2 equal to 0. Well, on both sides, so it's A times 0, which obviously is still 0, right? So if you do that, you get A1 A x1 plus A2 A x2, right, equal to 0. So this one will give you A1 lambda 1 x1 plus A2 lambda 2 x2, right? 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 So far so good, right? So, if that's the case, let's consider this equation and this equation. Okay. I mean, basically, it's like right? 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 So this determinant is obviously non-zero, right? This determinant is obviously non-zero, right? Because this, or I can get A1, A2 out of the determinant. So determinant of this one equal to determinant. I get A1, A2 out of it. A1, A2, determinant. 1, 1, lambda 1, lambda 2. So what is this? This is lambda 2 minus lambda 1, right? 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 Any question with that? No question, right? So we know, like, because we know, like lambda 1 is not the same, and the lambda 2 are different, right? So this one is not zero, right? Okay. So the only case for x1, x2 to have non-trivial solution would be either, A1 or A2 to be 0, right? But if A1 is 0, the other one is forced to be 0 as well, right? Okay? So, well, it's once you get these two, that's so easy. Either you do this or you multiply this one with lambda 1 and subtract the second one, whatever you want to do it. Basically, it's trivial. Okay, so anyway, just want you guys to know. Okay, if two vectors, for two eigenvectors, if they have different eigenvalues, they must be independent. Okay, so that's the first thing. And then, obviously, you can, apply similar concept to, do induction. You can do the induction. Okay, because for independence, you have to basically discuss at least two vectors, right? So base case will be what we just discussed, right? That's the base case. Okay, assume if you have k eigenvectors with k different eigenvalues, they are independent. Now with another eigenvector that has different eigenvalue, you just try to extend one more step. The process is similar. So I always just skip. For you guys, you guys can try to prove this by yourself. Okay? So here is the part I think is the most interesting. Okay, probably today. Okay. So the eigenvalue has something to do with determinant and trace. Okay, if A is the n times n matrix, the trace of A denoted as TRA, okay, is A11 plus A22 plus blah blah plus ANN. So just the sum of diagonal elements. Okay, the sum of diagonal elements. So if an n times n matrix A has n distinct eigenvalues, okay, be careful, okay? This is not necessarily possible. Okay, for example, for example that we have, this is 3 times 3 matrix, right? But how many eigenvalues do we have? How many distinct eigenvalues do we have? We only have 2, right? Okay, so you can see that, okay, this if is not necessarily always the case, okay? This if is not always satisfied, okay, this if condition, okay? If an n times n matrix A has n distinct eigenvalues, lambda 1, lambda 2, blah, blah, 2, lambda n, but if this is the case, we could prove that the determinant of A equal to lambda 1 times lambda 2 times blah, blah, times lambda n. Okay, we can prove this directly. Okay, the determinant, which is the multiplication of these n eigenvalues, and also the trace of A, which is the sum of the diagonal elements, will be the sum of all these n eigenvalues. Okay, these two properties are very, very interesting. How do we prove it? Do we have, yeah, here. So because we want to say, like, I mean, this, they are eigenvalues, right? So obviously, like, if the original matrix is A11, A12, blah, 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 A22, blah, 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 ANN1, ANN, okay, and the determinant of A minus lambda I will look like this, right? It will look like this, right? Any question with that? Huh? 哦，这边有错，对 ，it should be 21, it should be A21. Yeah, but you get the idea. Okay, sorry. Okay, but only this one is wrong, right? All the other part remains, correct, right? Okay. So here is the thing. This is probably difficult to observe. Okay, I will probably have to ask you to look carefully here. Okay, I mean, 这个可能用中文讲可能比较简单。Okay, here's the thing. Okay, 这边我们知道这个 determinant is how should I say, like n times n, right? So it could be very big, right? So we have to, when we compute the determinant, we have to follow the definition of determinant, right? So definition of determinant tells us that we need to do this recursively, right? 我们必须要就递回的来展开，才能得到 determinant 嘛，对不对？ So let's just pick the first column to expand it. Okay, you could do it. Other way. For example, use like the first row to expand it. That's also fine. But you have to use either the first column or first row. Okay, there's a reason behind this. Okay. So let's use first column. So it will be A11 times minus lambda times determinant of M11, right? You know this M11 notation, right? That's like you get rid of first row, first column, the rest of like the stuff, plus AI1, okay? Because we are talking about the first. Let me see, I1. This expansion is on the first row. Sorry, this is not the first column. This is first row. Okay, using the first row. Okay, so it's a summation a I1 times -1 I plus 1. Okay, determinant n1 I1. Okay, from I equal to 2 to n. You know that, right? So this is just like the definition of determinant computation, right? So far so good, right? Okay, so then it becomes tricky here. The next line, it will be this expansion eventually will become this. Why?为什么？Okay, we know that. Okay, lambda 1 to lambda n are distinct eigenvalues, right? So let's not look at this last line. 我们先不要看最后一行。这个展出来，上面这个展出来是不是一个浪达一个就是多项式？这没有问题，这不会有问题吧？上面展出来是一个浪达多项式，这没有问题，没有问题吧 ？OK， 然后它次方是什么？我没有你看最后一行哦，我要你看上面这一行，或者你就看这个啦，看这个，它最高的浪达最高次方是多少 ？n 嘛，对不对？一定是 n 嘛，对不对？好，那我接下来的就要问你们了 ，OK， 既然它次方是 n， 那它有 n 个解。那它展开来是不是一定是长这个样子？你先不要看这个，展开来它一定是有这个东西，它才会有这个解嘛，这没问题，这没问题，可以吗？那你说，那你说不对啊？那前面这个为什么是负1的 n 次方？是这样子的。其实 let's focus， 我们就只关注在一个东西上面就好了。什么东西？就是浪达 n 次方。我刚刚不是讲说这个是一个浪达 n 次方多项式吗？好，那我就问大家，浪达 n 次方的那个项，那一项，它的 coefficient 是什么？因为你看下面这边，你先把这个遮掉。浪达的 n 次方乘出来一定是1嘛，浪达 n 次方乘出来是1嘛，对。那我们现在重点就是这上面乘出来浪达的 n 次方那一项，它的 coefficient 是什么？对不对？好，那我先问同学一件事情，这边有没有可能有浪达 n 次方？有同学摇头说不可能，为什么？我们拿一个例子来看一下好了 ，OK， 我们拿第二项好了 ，A12 这边 A12 ，OK， 乘上要一个减啦，没关系，先那个加减先不重要，先看 A12， 你要把第一个 row， 那第二个 column 给它拿掉，所以你剩下来是这一部分。跟这一部分，对不对？这一部分，你注意一下哦。你拿掉这些了以后，你这一项是不是被拿掉了，对不对？这一项你拿掉了这一个项跟这一项，对不对？对，你拿掉这一项跟这一项，所以拿掉2个浪达，对不对？2个浪达，你剩下来的，事实上呢，最多只能让你乘出来。浪达的 n 减2次方 ，OK， 最多 你另外第 A13也一样，你拿掉这个，它对应的那个 column 的一个 A33减浪达，跟拿掉这个 A11减浪达，也是一样，你最多只能乘出来一个最高的次方是浪达 n 的浪达的次方是超过 n 减2次方的，这没问题。可以吗？所以我再问一下，浪达的 n 次方，你只能从哪边去找 ？When you want to look for lambda to the power of n, the only place you can look for that term is here, right? 好，那再下来，好，那这边有一个负浪达，对不对？然后你这边也还是一样嘛，你这个地方。好，你把第一项拿掉，然后剩下第一个 column 第一个 row 拿掉，然后再来，你就又变成 A22减浪达跑出来，对不对？然后你A2减浪达 A33减浪达点。那当然还有一些其他的 term 啦，我不是说这是唯一的，但是你还有一些其他 term，但是跟浪达相关的就直接，那你去看，这每一项就有一个减浪达，那总共有 n 个嘛，所以它会有负1的 n 次方。OK， 所以这个展开来 ，eventually 会变成这样子。OK， 或者我如果说我写的更直接一点，我如果说不要这样写，我可以写这样子。其实我写的，我不要去考虑那个什么负1的 n 次方，我其实就是写说这个。因为它都是减浪达嘛，我就保留那个就好了，我就连那个负1的 n 次方都不用去考虑了，对不对？就是这样子啊。讲到这边有问题，好，所以 ，OK，if you guys agree with me。Okay. The next part is the magic. Okay. The next part is the magic. So we have this, right? 我们有这个，对不对？ Then if I put 0 into lambda, what happens? The left side, because if I put 0 into lambda, the left side becomes determinant A, right? Right? The right side becomes what? Lambda 1 times lambda 2 times lambda n. Right? Right?所以我就拿到了第一个 the first one I want to prove. Right? Okay, so the tricky part is to first admit this determinant. Actually, after expansion, it looks like, well, I mean, either this one or this one. Whatever you want to, you want to write it down. Okay? How about the second one? Trace A equal to lambda 1 plus lambda 2 plus lambda n. 我问同学一下，我把这个先擦掉。这个我们大家现在已经同意了嘛，对不对？这个我们已经同意了。好，那我们可不可以稍微展开一下？它的第一项是不是负1的 n 次方，浪打 n 次方，对不对？对不对？第二个呢，浪打 n 减1呢？浪打 n 减1呢？浪打 n 减1是不是你选？是不是浪打 1 加浪打 2 加浪打 n 的浪打 n 减1次方？应该是有个减啦，我看一下。这边应该有个负1的 n 减1次方。对不对？对不对？后面就不重要了，后面就不重要了，加点。OK， 好，到这边还好吧？就是你只展开前2项嘛。第一项是浪打的 n 次方，第二个是浪打 n 减1次方，从这边展开，从这边展开，这个展开会展哦 ，OK， 这展开会展哦，大家会展开嘛，对不对？那第二项是负1的 n 减1次方，然后乘上刮弧浪打1加浪打，这边就这个就跑出来了，然后乘上浪打 n 减1次方，对不对？对。好，那接下来我们要来比较。The next step, we compare. 我刚刚是不是有跟大家讲过？这个里面会有很多项，但是这里面的项不会有浪打的 n 减1次方跟浪打的 n 次方，它最高就是浪打 n 减2次方，对不对？所以浪打的 n 次方跟浪打 n 减1次方都只会在这个里面跑出来，对不对？对不对？然后呢，你反复这样继续往下展开来，你会发觉说这边出来的结果会是，就是说浪打的 n 减1，应该说 n 次方跟 n 减1次方。它会出来的项哦，就是 A11 减浪打，刚刚不是有乘上一个 determinant n1 吗 ？n11 吗？对不对？你这可以继续往下做，这边会再跑出来 A22减浪打，然后再乘上一个 determinant， 再小一点的，对，然后再继续做，就跑出来点，就变成这会。就是说，其他有没有其他项？有其他项，但其他项不会出现浪打的 n 减1次方跟浪打的 n 次方，所以你会出来浪打 n 次方跟浪打 n 减1次方，只会出现在这个 A11减浪打 A22减浪打点到 ANN 减浪打这一项里面。OK， 你可以反复展开嘛，这边再继续展开，再展开一次的时候，就是你同样用第一个剩下来的第一个 row 去展开，就会跑出来 A2减浪打，然后这个变小，然后再用那个剩下的再展开一次，就是一直展，那就会你会发觉说有浪打的 n 次方跟浪打 n 减1次方的，就只会存在这边，后面有一堆垃圾啦，那垃圾不用管它 ，we don't need to care about those because here we only care about 浪打 n minus one， the order of 浪打 n minus one， OK，so，所以重点是这个东西乘出来，它的浪打 n 减1次方的 coefficient 是什么？是不是也是？是不是刚好是-1的 n 减1次方乘上 a11 加 a22 加点点点加 ann， 对不对？那你这样两个一比，这个是不是就应该要等于这个？对不对？This proof is very interesting. It's really not very sophisticated, but it requires a lot of observation. 就你觉得要能够看清楚，你把它展开来的时候，你想想看啊，这些没有浪打的 n 减1次方，浪的 n 次方的，所以那都可以拿掉，不用管它。那意思拿掉，不用管它。那剩下来的你去看。那浪打的那个，当然浪打这个乘的这个东西比较直接啦，你就是把浪打带0进去，你只要知道说这个东西是它 determinant， 你把浪打带0进去就直接得到。那第二个就比较麻烦，你要稍微看清楚 ，you have to find out that okay, I mean really like there's no any term okay. With lambda order greater than n minus 2 here， 就是你这边的那个 order 不会超过 n 减2，sorry， 不会超过 n 减2啊，不会超过 n 减2，就是这个可以反复这样做下去。OK， 那这边你每展开一次有一些就扔掉，先不用管它。那直到说，展出来剩下来的是这个东西。那你的浪打的 n 次方跟浪打 n 减1次方都从这边来，所以两个一比，你就会得到这个 trace A 会等于浪打1加浪打 n。However, let me make it clear again. Okay, this theorem comes with a condition. Okay, 这个 condition 就是你的 n 乘 n 的 matrix A has n distinct eigenvalues. This is not necessarily always the case. To be honest with you, okay, a lot of time this condition does not satisfy. OK， 这个 condition 通常在很多的例子里面是不成立的。所以虽然说这个有很漂亮的东西，但是呢，事实上你用到的机会其实比你想象中的少。OK， 但是这个当他们就是每一个 eigenvalue 都不一样啊，这有很好的性质。OK， 好，我们休息10分钟，好不好 ？Let's take 10 minutes break。那回来，我们应该差不多在11点半开始考试哦。那个大概还有个20分钟左右，那个可以。上一集。我知道。等一下。